So in this problem, we are asked to find the magnetic field at a point P, which is along the axis of a given loop of a wire. Remember, in the previous video, I actually solved a similar situation in which I had a full loop of wire and I was trying to find the magnetic field at the center. So at the center of the loop, we obtained an expression for the magnetic field to be mu 0 I over 2a, and this was actually derived from the study of a single small arc. So at the center of an arc, by using the Biot-Savart law, we were able to obtain B to be equal to mu 0 I over 4 pi a times theta. And to find the magnetic field at the center of the loop, we just substituted theta by 2 pi. Theta is basically the angle formed by the arc. So for a full circle, theta would be 2 pi, and then this equation would reduce to this expression here for the magnetic field at the center of a loop. But right now, we are moving to a more sophisticated situation in which we are studying the magnetic field not at the center, but at a point along the axis of the loop. So we are interested with this point P now instead of point O, which is the center of the loop. So I have a figure here showing me the wire, which is forming a circular loop, the point P of interest, which is right here, and I have taken an infinitesimal length of the wire, dl, shown here. You can see that dl is going to be in this direction according to the direction of the current, which we can see. So this is the direction of dl, which we named to be ds in the previous part, in the previous video actually. The direction of the unit vector r is as such, and if we use the right-hand rule to check for the dB direction, for the direction of the magnetic field associated with this infinitesimal current and the corresponding R, you will see that the obtained direction for the magnetic field is as such if you use the right-hand rule, in which your thumb points along dl and your index points along R, and then you will be able to find the direction of dB to be as I have drawn here at point P. Now, as you move along the wire at different points, you will see that different points will give you different directions for dB. dB will range along these directions. However, you will see that to find the total magnetic field, you will see that the y components of the infinitesimal magnetic fields cancel out as we integrate along the wire. Whereas the x components add up. That's why when I solve for the magnetic field, I will actually integrate. So again, I have here mu 0 I over 4 pi integral of dl cross r, which I will write as dl over r squared, multiplied by cosine theta, where theta is the angle that dB makes with the horizontal. So I will just integrate dB with considering that the x components add up, whereas the y components cancel out, and thus the obtained magnetic field is along the x-axis, so I can just multiply dB by cosine the angle theta here formed with the x-axis to obtain dB along the x-axis. This is the x component of dB, which will give me the net value of the magnetic field. So with this, I can proceed to check the variables I have in order to solve this integral. I can see that dl, its direction is shown here. However, a side view of the loop will be more convenient for me to be sure of the directions and the angles associated with the magnetic field. So this is point P, this is the x-axis. Like we said, dl is the infinitesimal current, which, according to the side view, will be pointing outside the page. Whereas r, which is the unit vector pointing along the distance between dl and p, will have this direction. You can see that dl is pointing outside the page, so it will be perpendicular to any vector inside this page, including the unit vector r. That's why I just substituted dl cross r by dl alone. The angle theta is 90 for this infinitesimal current. I did multiply by cosine theta in order to account for the x component of the magnetic field only, because this is what will add up for the total magnetic field. Now, if I look at the angle theta from which I'm going to solve cosine theta, the angle theta is this angle. However, to solve for this angle, I don't have any triangle associated with this angle. That's why I'm going to relate this angle theta to theta prime here. So theta prime is actually 180 minus theta minus 90, where 90 is this angle here. So I will obtain that theta prime is 90 minus theta, and thus cosine theta will actually be equal to sine theta prime. So this will give me mu 0 I over 4 pi integral of dl over r squared sine theta prime. Of course, as we move along the wire, theta prime is changing. However, theta prime for this infinitesimal magnetic field is equal to sine theta prime will be equal to the opposite over the hypotenuse. The opposite side is basically the radius of the loop, whereas the hypotenuse is this distance r. So I can write this as mu 0 I over 4 pi integral of dl r over r, and I have r squared here. This gives me mu 0 I over 4 pi integral, I can take r outside, and I will obtain an integral of dl over r cubed. I can see that I can write r cubed in terms of capital R and the distance from the center to the point P according to the Pythagorean theorem. R squared is equal to capital R squared plus this distance here, which is x. So R will be radical R squared plus x squared. So I'll have mu 0 I r over 4 pi integral of dl over r squared plus x squared power 3 over 2. So now that we have obtained this form for the magnetic field, we notice that the integral is actually over dl, whereas the quantities we have in the integral are basically r squared and x squared. And if we check our figure, we can see that over all of the length of the wire, the values for x, which is the distance from the center of the loop to the point P, and the value of r, which is the radius of the loop, are fixed. They do not change. So r and x do not change, which means that we can take them outside of the integral, and we will obtain an integral over dl only, where dl actually goes over the circular wire that we are studying. So dl will be an integration over all of this circular wire, and it will basically be equal to 2 pi r, which is the circumference of this circular wire. And so we can find our final expression of the magnetic field, mu 0 I r squared over 2 into r squared plus x squared power 3 over 2 as required in the question here. Now in part B, we are asked what's the magnetic field along the axis if r is much greater than x. So if r is much greater than x as asked in part B, we can see that x squared will be negligible if r is much greater than x. And this means that B can be written as mu 0 I r squared over 2 into r squared power 3 over 2, which gives us mu 0 I r squared over 2 r cubed, which is mu 0 I over 2r. This is basically the magnetic field that we obtained when we were studying the center of a loop, mu 0 I over 2a, where a was the radius. We got the same expression, and this makes sense because if r is much greater than x, then we are so close to the center of the loop that we are almost at the center. So we're almost at this point. Okay, so the magnetic field reduces to the expression of the magnetic field at the center of a circular loop. To solve for the integral. Another special case of our study of the magnetic field generated at the axis of a coil is the situation where r is much smaller than x as given here. So we want to compare the magnetic field formed such that r is much smaller than x. So I can recall first the equation of the magnetic field that we obtained for the point that is along the axis of a coil. So for a coil of radius r, B at a point which is at a distance x on the axis of the coil has this expression. Now for r, which is much smaller than x, we can see that B reduces to the following expression. And we can see how the magnetic field has a new form. This is when we have a very small coil and the distance x is pretty large. So this is x, whereas r is this tiny distance here. So here r is much smaller than x. Now there's something that we are asked for here also, which is what is the equation of the magnetic dipole moment? So actually the magnetic dipole moment generated by a coil can be obtained by rearranging this equation to be in terms of the area A. I can substitute r squared by a over pi, then the magnetic field is mu 0 A over 2 pi x cubed. The magnetic dipole moment is actually simply this quantity here, which is I times A. And note that if I had n turns in this coil, then B will be mu 0 n IA over 2 pi x cubed, and here mu would be equal to ni times A. And this gives me mu 0 times mu over 2 pi x cubed. This is the magnetic field that we obtain if x is much larger than r, so that we can say we have a magnetic dipole. So basically the magnetic dipole is the situation where the coil is small compared to the distance at which we are checking the magnetic field. Or the magnetic field has to be strong enough so that it can be exerted at distant points where again x is much greater than r.